and I told you how this helps in basically localization and mapping, right? And I started with encoders. I said basically the encoders are the most important, and we call these as quadrature encoders. And why do we call it a quadrature? Because it gives you basically two pulses, right, which is exactly 90-degree apart. Quadrature, right, exactly 90-degree apart. I told you all these, right? Right, with one slots we will not be
Yes,
able
sir.
to, yeah, very good, we will not be able to find basically the direction. In order to understand the direction, we have two slots which is exactly electrically and mechanically 90-degree apart, right? Now I just wanted to show you literally, like, I wanted to show you the disk which we have in our lab. But before that, what I'll do, I'll just take you to just when I type quadrature encoders. Are you able to see my screen?
Yes, sir.
Yeah. So if you just type in quadrature encoder, you'll get basically this. Okay, this is what I was saying. Basically, you will get two pulses, right? When you have a clockwise, you'll have A leading B. When you have an counterclockwise or anti-clockwise, you have B leading A, based on how this, slots are arranged. Now, if you go down, you will be able to see even how the slots are arranged also. If you could see here, this will be able to really, you will be able to understand like how this encoder really works. Okay, because you could see here you have a light source, you have a receiver, the light passes on, and think of this as only one slot, right? This has only one slot, and this is how it is. Now think of, if you see here, position encoders, if you see here, this, if you see the slots, these slots are the way like exactly approximately 90 degrees apart, right? So this is how basically this encoder looks like. And if you see the number of pins basically it has, as it's shown here, basically it has basically four pins. Okay, I'll tell you what are the pins back here. I'll show you. I think yeah, this is what it is basically. If you see it, can you see it? Make your own quadrature. We made like this only basically, right? So you have basically, these are basically like receivers and the transmitter basically, and you have multiple slots here, which is exactly like electrical 90 degree. Right? So I'll go back to the PPT and just tell you. Right now, how does this encoder look like? So what I'll do, I'll show you a robot in our lab which has this encoder, but you cannot see the encoders directly. So what I'll do, I'll just show you like how those pins look like. So I'll switch on my camera. Let me know if you're able to see me, or I just need to adjust my camera or not. You just let me know. Are you able to see me at least? Right?
Yes.
Yeah. I'll just show you my robot. Are you able to see this robot? Right? This is basically a mobile robot which we have in our lab. Are you able to see this mobile robot?
Yes, sir.
Yeah. Now think of, as of now, what we learned. Okay. Now think of, as of now, what we learned is, given a global frame, that means the global frame will be somewhere in this room somewhere, right? You have a global frame which is assigned, right? So that means it's an inertial frame. Now what did you do? You assigned a robot frame which could be over the chassis, and it has a controller. You could see basically a controller board over it. It can be just below the chassis somewhere. You would have fixed a robot frame. Now you have two wheels, right? So what did you do in the kinematics? Think of, you learned about this wheel kinematics also. But overall kinematics, what did you get in the overall kinematics? Can anybody just let me know, like, what did you learn in the overall kinematics? What did you do basically? What did I do in the overall kinematics?
The angular velocity with respect to the robot
Very
velocity.
good. So that means I I had this robot velocity with respect to the frame which I had assigned. So that means the robot speed, when I say it's basically along x-axis, it can be a rotation, right? And also along the y-axis. Y-axis, please understand, it will not have a direct translation. Please understand, it cannot have a lateral, right? Lateral velocity, but it could do a kind of an both, right? Omega as well as uh, x put together. It can do basically a y, right? Now, so what you were really doing, you were converting this robot velocity to the angular velocity of the wheel, right? So what you have now, you have a relationship where a user, if a user gives, I want this robot to move at x-axis at 30 meter per second, or 10 meter per second, or 5 meter per second, whatever it be. If I say that, and now I'll be able to really compute how much should be my angular velocity of both the wheels, right? And where is my both the wheels connected? If you look at the down, could you see here two motors? Could you see two motors here, right? So
Yes,
they
sir.
will, now it is attached to the motors. Now, what you know is, what is the angular velocity at which this motor should move or rotate? Make sense? Now that means now your controller is ready to understand like what should be the angular velocity which you had fed in. Now what you have to do, you have to adjust or tune something based on the driver or something so that you achieve. You have to map a certain value so that it really achieves this angular velocity. Now for this, now for understand, for the closed loop control, if you want to have a closed loop control, maybe a velocity control, maybe a position control, you need to have an understanding of where is my robot. Now rather than using a kind of an overhead camera or something like extroceptive, now how do you really identify the robot is you use this joint encoders. That means what you do now is like from the joint values whichever is given to you, you calculate the robot position. Did you learn any equations to do that? Yes, the same kinematics, right? Now think of the kinematics can be used in two ways, inverse and forward. One way is like for the control, please understand, for the control, what I will be giving is I'll be giving the robot velocity from which I'll be computing this joint velocity. On the other hand, through the sensors, I know basically my joint velocities or my wheel velocities from which I need to compute my robot velocity. Can I do that? Yes, right? It's just taking an inverse or like just multiplying the Jacobian or whatever the wheel configuration matrix, right?
Yes, sir.
Yes, please understand. Okay. Now, what is important to me to understand what is the angular velocity or what is the position of the wheel. So, in order to do that, we have encoders. If you could closely watch here, I don't know whether it's visible or not. Which side will be visible, I do not know. But I'll just try to show you basically if it's visible. If you see closely watch here, could you see a small wire going out here? Could you see? Right? If what I'm really touching, could you see basically wires?
Yes, sir.
Yes, right. Now what you have here is like in this motor, okay, in this motor, if you could see basically a black color, can you see a black color attachment here, which I'm pointing out? A black
Yes.
color attachment, that is basically the encoder. And from the encoder, if you see, these wires are coming out, and these wires are connected to this controller. If you see at the bottom, I don't know whether you'll be able to see that, this wires goes to the controllers. And what does this wire has is like this wire has, this is basically a collection of 4 wires. If you see, I don't know whether you will not be able to see, I think, the 4 exactly wires, but please believe me, it has 4 wires, right? So that means please understand it has an encoder, which is an quadrature encoder, and you have a disk, which is the black one. You have a disk here, and from the disk 4 wires comes out and you're connecting it to the controller. There are two things which we need to understand. One is principle of working, which I already said. Okay, so now think of, I cannot sit and say like it has optical encoders and it has Hall effect encoders. So all these principles, I don't think I need to teach you all these. But rather than that, whether it's an optical, whether it's an Hall effect, whatever it be, I need to give you an understanding like how do we really decode it into position, right? So I'll teach you that. You understand whichever the quadrature encoder be, I have 4 wires coming out of it, right? Now what we will be learning is like what these 4 wires are meant for. And you know that I'll be getting 2 pulses, right? 2 square waves, which are exactly 90-degree apart. Now, out of that 2 square waves, how do I really compute position? Now, after we compute the position, then we'll understand like how do we really compute the velocity, right? We used to give this as a part of experiments even, where we used to teach them this algorithm and we asked the students to do that on the controller on their own, starting from the very basic. Okay, we don't give them any functions or something. We ask them to do it with the boolean whatever we teach. We ask them to do that in the controller. Okay? And we used to make them just ask them to rotate these wheels, and we used to have a markers placed over, right? We used to have a markers and we'll ask them to rotate to 90 and see whether you are exactly getting 90, something like that. Okay, and we used to also motor, we used to give a voltage to this motor so that it rotates, and we used to have a tachometer, and also we used to see like is the velocity which we calculated from the encoders and the velocity which tachometer gives is approximately the same. So these basically experiments, these are markers basically which we used to use for the tachometer as well as finding the positions, right? So this is what we used to do. Now I'll just help you out in understanding like how do we really use this algorithm. Okay, right? So I'll just share my screen now. Okay. Okay. Is my screen visible? Yes? Is my screen? No? Oh, sorry. Now?
Yes, sir.
Yeah. Okay. Now let us understand, right? So what are we going to learn now is very important in robotics, right? Where because most, whether it's a manipulator, whether it's a mobile robot, whichever it be, the most important sensor which comes in the robot is encoders. Okay. So we are talking about quadrature encoders. So what are we going to learn is what is basically how do we really decode, how do we basically decode the position or velocity, right? So we'll understand this. Now, in general, I told you, uh, quadrature decoder will have two slots which are electrically or mechanically 90-degree apart. So I will generate basically two square waves, right, which is exactly 90. Right. Right. So this is called as channel A. This is called as channel B. Now this quadrature encoders will have basically four wires. The first wire is for the positive because it has an LED and a photoreceptor for that power source. It has uh, two wires for its power, right? And other two wires, which is channel A, we call it as channel A, and we have channel B. So this is what all the four wires are. Okay. So what are we going to do is like we are just going to tap this channel 3, wire 3 and wire 4, which we call as channel A and channel B, and we will understand like how do we really convert these pulses to a position or a velocity, right? So the encoder decoding is basically classified into three types. So they are classified into three types. We call it as X1 decoding. We call it second as X2 decoding, and the third is X4 decoding. Right? Now, I said last time, last class, what are we going to measure in this? Now think of, many of you said like I'll count the pulses, right? I think many said like I'll count the pulses. Now when I say pulses, what do you think as a property of pulse? What all things you can count here? Please understand. I can count basically the low state, right? See, any pulse which I'm talking about, please understand any pulse which I'm talking about. I have a low state, I have a transition state, I have a high state, again a transition state, right? That means I have a low, I have transition T1, I have high state, and I have basically again transition T2 because these two are different transitions. It starts from 0 to 1 and this transition starts from 1 to 0, right? Now think of, if I really want to count the pulses, either I can count the number of lows, make sense? Or I can count the number of high, or even I can count the number of transitions. Is it clear what I'm saying, everyone?
Yes, sir.
Yeah. If you don't understand, please let me know. Okay, please don't keep mum. Okay, please let me know that. Okay. Now, which one is good to count? Now, please understand. When I count only low and high, the problem here is like always the sensor is prone to noises, right? So when I have only low, that means I should ensure that even if noise comes in, there is no transition from the 0 to 1, because most of the time counting only the low always ends up miserable. Something or the other will end up counting like it is not low. Okay, so in case of robustness, it is always better to count the transitions. Now that means I'll eliminate low, I'll eliminate high, so I am only concerned about the transitions. Now when I say transition, please understand, when I say transition, I have two transitions, T1 and T2. So similarly, now think of how many channels I have. I have two channels where channel A will have two transitions, T1 and T2. Similarly, channel B also will have two transitions, which is T3 and T4. Make sense? Yes or no?
Yes, sir.
Now, how many? What are the various opportunities do you have to count? Think of. I have basically nothing of. I can count only T1. So that means I'll count only the rising edge of A. I can count both T1 and T2, right? Or the other option is like I'll count all T1, T2, T3, T4. Does it make sense? Are you getting what I'm saying?
Yes, sir.
Yes. So based on this, that's how we classify X1, X2, and X4 decoding. What do you mean by X1 decoding is like when I count only one transition. Okay, please understand it can be higher or lower. I'm counting one transition of one particular wave. So that means, example I'll put here, I'm going to count only the rising edge, that is T1 of my channel A. And this is called as X1 decoding. So now X1 decoding, I will only measure one transition of only one channel. Mostly I'll say like rising edge. So rising edge is T1, which goes from 0 to 1. So I'll be counting only 0 to 1. Whether if it is 0 to 1, I'll increment by 1. Is it clear? If it is not, I'll not do anything. So that means I'll just count on T1, how many T1s have happened, and I'll use that to find out the position. Now, what do you mean by X2? Example of X2 is like for the same wave, please understand, for the same channel, I'll count both T1 and T2. What does it mean? I'll count both the rising edge as well as the falling edge. Clear? Right? Now, what is X4 decoding? Can anybody guess? What will be X4 decoding then? X4. Think of 4. What will be X4 decoding then? Speak out, guys.
T1, T2, T3, and T4.
Yes. So what I'll be doing, I'll be counting all the transitions. That means I'll count basically the transition T1 and T2, right, of my, that means it is rising edge as well as falling edge of my channel A. Similarly, I will also count T3 and T4, which is rising and falling edge of my channel D. So that means I now, in the previous X1 and X2, I was only concerned about one wave. Please understand, I was only concerned about one wave. Now what I am doing right now is I'm concerned about, in X4 decoding, I'm concerned about both the wave, and I'll count all the transitions of both waves. Now which one do you think is better and why? I'll give a clue in terms of resolution, at least you tell me. Which one do you think is better and why?
X4 is better.
X4 is better. Very good. Why? Any idea?
If you want to increase or decrease your encoder, you have to consider both the. If the robot is moving forward or backward.
No. That is different. Okay. Now, yes, your confusion. I understand your confusion. Your friend's confusion is if I use X1 decoding, he is assuming like I'll not be able to count the direction. Please understand, all this decoding which I told here is just to count the position. So that means it doesn't really impact what is the direction. See, please understand, whether it's an X1, X2, and X4, I will be calculating the direction, right? This is just the method to understand like whether I should increment the value or decrement the value, right? Now, this is just the method to understand to increment value. For example, if T1, now think of, if T1 appears, I'll do +1. Again, T1 appears, I'll do +1. So when will I do -1? When I say that direction is changed. If the direction has changed, I'll do -1. But see, this one which I'm talking about, the count, I will only count this T1. That is what X1 decoding means. But for all this X1, X2, X4, which I'm talking about, everything will measure direction. Is it clear what I'm saying? No confusion. Everything will measure direction. This is just, I'm telling you how many pulses will you count? For the same pulse, how many elements of the pulse you will count? So in the X4, you will count basically 4 elements of both the pulses. Now think of which is better. X4 decoding is better. Why? Think of in the X1 decoding for the same 360 degree. Okay, when you have a 360 degree rotation. So when I'm counting only one transition, what does that mean? For example, I say for one transition for 360 degrees, for X1 decoding, it gave me 100. For the same 360 degree, if I do X2 decoding, how if it's 100, how many counts will I get for X2? How many counts?
200.
200. How many for X4? How many for X4?
400.
400. Why? Because I'm counting 4 states here. For X1, I'm counting only 1. So that means 100. So if I'm doing with X2, the 100 got improved to 200. Now, which has the better resolution? X4 has the better resolution. Why? The complete 360 degree now it can be resolved or can be divided into 400 parts. Are you able to understand? Where here I'm, see, now think of what is the resolution here? How will you find the resolution? What is the resolution? See, 360 by 100, how much is that? 3.6 degrees, right? Is it clear what I'm saying?
Yes, sir.
So that means the minimum count which my encoder, if I use X1 decoding, will be only 3.6 degrees. But if I use the same X4 decoding, the same, now think of 360 by 400, it would have improved. So that means X4 decoding gives you better resolution. That's where X4 decoding is very popular, right? Now, how do we really use this X1, X2, X4 decoding? Okay, so I'll start with X1 decoding. Now, whichever decoding be, I have to do two things. One is count the pulse. So when I say count the pulse, which to count? Whether it's only the transition, upper transition, rising edge, or the lower edge, all these is denoted by what decoding I'm doing, whether it's an X1 or something. So when I use X1, what do you mean by count the pulse? I'll use only the rising edge, right? I'll use the rising edge of only one channel. So I'll say here channel A. Make sense? Because it's an X1 decoding. Second, I need to have the direction, right? So I need to do two things. I need to understand like which property of the wave I should count, which state I should count. Second is how do I really find the direction? So let me give you an understanding. So what am I really counting? I'm counting a transition. So based on, so I'll use the next page. Okay, so I'm going to teach you X1 decoding. Now this algorithm, whatever I'm teaching now, is not mandatory that you have to use only this algorithm. This is the algorithm which we have developed and we are using it in our lab as well as for our projects. So this is a simple algorithm which we felt is easy for the students. Okay, so if you ask me like, is there no other solution? There are solutions, but this is one of the way which we have framed for you. Okay, that's it. Okay, now X1 decoding, I'm drawing the wave. Please be attentive in this. Right, I have a channel A, I have a channel B. Is it right? Okay. Now in X1 decoding, what am I really counting? Please answer, guys. Okay, it's very boring. It's very monotonous if you don't answer anything. What I'm really counting in X1 decoding in this entire thing, both the way.
Sir.
T1, sir.
A, right? So what I'm counting? I'm counting T1, right? So that is a transition from 0 to 1. I'm only concerned about this transition. No other transition I'm concerned about. So first I'll teach you how to do this count. Then I'll come back to the direction. So now direction means I have to compare both A and B. Otherwise, I'll not be able to understand the direction. But for the count, I'll only take channel A, right? Okay. Now, you know that only the states which I have with me is 0 and 1. So for which, now think of, I have 0 and 1, two states. So what are the various combinations I can have from 0 and 1? I can have 4 combinations, right? Either I can have 0 0, I can have 0 1, I can have 1 0, or I can have 1 1. Now what is a 0 0 state? 0 0 state is basically this. Now what I am saying this is, think of this is previous state of A. This is present state of A. Because I'm concerned about only A, channel A, right? Now think of if my previous state of A and present state of A. So I have basically these 4 combinations. So what do you mean by previous state A and present state A both 0? What do you mean by that? It's a low state, right? Because you think of previous as well as the present is both 0. Yes?
Yes, sir.
Now in this combination, which gives you basically the transition? Which combination gives you transition? Will 1 1 give you a transition? No. 1 1 is what? 1 1 is my high state. So that means in this entire combination, I'm not concerned about these two at all. So what am I really concerned about? So these are basically a kind of a don't care. I don't care at all. I'm only concerned about this, right? What is 0 to 1? 0 to 1 is what my upper transition is, T1. Right? And what is T2? T2 is the transition which is my this, falling edge, which is from 1 to 0. Yes or no?
Yes, sir.
Yes. So have you seen kind of such, if I ask you Boolean, have you seen any kind of an gates logic based on this, where you get only one for, that means if I'm only concerned about this transition and I want, if this transition happens, I want to raise 1 or I want to get output as 1. What kind of a gate can I use?
Or
Hmm?
or gate.
OR gate. Now think of in the OR gate, will this 1 1, what will be this 1 1 also? 1 1 also will be 1, right? So do I really require it? I please understand. I want this 0 0 to be 0 as well as 1 1 to be 0. I only want 1 when I have only the transition.
Sir, XOR, sir.
Very good answer. It is XOR, right? Now think of if I use an XOR, and pass this previous and the present state of whatever the channel be, I'll be able to really understand whether transition has happened or not. Does it make sense?
Yes, sir.
Yes. So very good. So what I will do, I will use an XOR gate. Okay. It would be very interesting. Like, I don't know if you could really, if you were here physically, I would have really taken you to the lab and we would have done it live basically. Okay. Now, yeah, now we cannot do that. Okay, just I'll teach you basically. Now, this is an XOR gate. So one of the input to the XOR gate is previous state of A, and this is present state of A. Now, what do you mean by previous state of A? I have to have some register or some variable where I always store the previous state, previous condition, okay, of the A, and I have other variable which gets updated with present. Okay. Now think of, if my previous state of A is 0 or 1 or 1 or 0, whatever it be, what is my output here? My output will be 1. Yes or no?
Yes, sir.
Yes, sir.
But for x1, do I really require both? Please answer it correctly.
No, sir.
No,
Only
very good, very good. So which one do I really want?
0 and 1, sir.
I want only this, right? 0 to 1, right?
Yes,
That
sir.
means the higher transition. So I'm only concerned about T1. If it was x2, I will take both. Now that means if I'm only concerned about this, I should make a logic in such a way, I should only get 1 when it is 0 to 1, and I should try to get 0 when it is 1 to 0. So what will I do, in order to get only 1 during this rising edge, I'll use another AND gate, right? And to this AND gate, what can I do? I will put the present state of A. Now think of, when will this final output be 1? Please understand. I'll redraw again the wave. So I have a transition 0 to 1, another transition is 1 to 0. For the XOR, 0 to 1 as well as 1 to 0 is going to give me 1. But for this transition 0 to 1, what is the present state of A? For this transition 0 to 1, if it would have completed the transition, what is the present state of A?
1, sir.
1. So that means what will be this? If I give an input present state of A, what will be this? This becomes 1.
Yes,
So I'll
sir.
generate 1, right? So that means for the T1, I'll get 1. But think of the T2. 1, 0. Of course, my XOR will give me 1. But what will be the present state of A? It has already reached from 1 to 0. What is the present state of A?
0, sir.
0. So what will happen?
It'll result 0, sir.
This will become 0. Now, will this logic help me to find out only T1? Yes, right?
Yes, sir.
Yes. So this is how we compute only the rising edge, only one rising edge of a pulse. Is it clear? Is it clear?
Yes, sir.
Now that means if I get 1, what will I do? I will just start adding or decreasing 1. So that means this is basically a condition to count, only count. Now what will be the condition for me to find the direction? Now for the direction, can I use only channel A or I have to use both channel A and B?
Both channel A and B.
I have to use both channel A and B. Now for which, what do I do? What we did was, in our lab, what we did was, we framed in such a way, if A is leading B, please understand, if A is leading B, let me get 1. If B is leading A, that is the opposite, let me get 0. Right? So only condition is like if A is leading B. In this condition, think of which is leading? A is leading, right? Because A is reaching the higher value before B. Right? Yes?
Yes, sir.
So that means when A is leading B, I should get 1. So first intention is for me to compare these two and ensure that whether A is leading B or not. Okay, so what will I do? Now, again, please understand, I am only concerned about this T1. So I will check whether T1, the condition of T1 is such that it is leading A or leading B. I'm not concerned about any other transitions because X1 is only concerned about T1. Okay, so that means this phase difference which I'm applying now is not applicable for all the decoding methods. As simple as that. So what will I do? I'll use the same XOR. Okay. So again the same. I'm redrawing it once again. So I have previous of A. I have present of A. So what this will give me? This will give me 1. Right? Yes. So this will give me 1 for both the transitions, right? Yes or no? Yes. T1 and T2, right? Hello?
Yes, sir.
Yes, yes. Now, what I will do, if A is leading B, I want to make it 1. Now, please compare these two waves. At this condition, A is leading B, right? So that means if I say my present state of A is 1, what is the present state of B at that condition? Because I'm only talking about this transition. I am not concerned about any other transition. I'm talking about only this 0 to 1. In 0 to 1 transition, what is the condition of B?
0, sir.
0, right?
Yes, sir.
So what will I do? Please understand. I'll use again an AND gate. And as I said, when A is leading B, I want 1. But I know my present state of B is 0. So what will I do? I'll put the present state of B to a NOT gate. And I'll mark it here. So that means, please understand, here it is present state of B. Now, will it give me 1 always if A is leading B? Please understand.
Yes, sir.
Yes, why? Because now think of, if this is 0 to 1, this is going to give me 1, right? And if I know that, now think of the present state of B is 0. So when I pass it to a NOT gate, it gives me 1, so 1, 1. So that means I understand whether A is leading B or not. If you have a doubt, what will I do? I'll draw another one which gives me B leading A. So how will I draw B leading A? So I'll have my B. This is my A. This is my A. Just 1 minute. Yes. Now think of when I draw this B leading A. Hold on. Yes. I'll have my A starting from here, right? Okay. Have my A starting. Right. So what am I really concerned with? I'm concerned with 0, 1, right? Now think of if this is B leading A. Now in this B leading A, what will be the output here? Output will be 1. Now in this condition B leading A, what is the present state of A? The present state of B? In this condition, what is the present state of B?
1, sir.
1. So when I pass this 1 to a NOT gate, what will happen? This becomes 0 and 1, 0 will become what? 0. Right? So that means it gives me an idea whether A is leading B or B is leading A. Make sense?
Yes, sir.
Yes. So this gives me the at what instant I should count, and this gives me the direction. Now what does this help me? Now that means if I get a 1 here, it ensures that I have to count, and this gives me whether I should count a forward or backward. So that means if A is always leading B, I'll start counting 1, then again plus 1, then again plus 1. Suddenly, if this becomes 0, what does it mean? Direction has changed, right? If the direction has changed, what will happen? What will happen? The same plus 1. That means again if the T1 appears, now I'll not have plus 1. What will I do? I'll have minus 1. Is it clear what I'm saying?
Yes, sir.
Right? So please understand, this gives me an instant when to count, and this gives me an instant should I count in the forward way or in the backward way. Is it clear? That means it's a direction. Got? Easy? Think of very simple logic. We created a very simple logic literally. Clear? Any doubt? Any doubt?
No doubt, sir.
Okay. Now the class is still 3 or 3:10.
3.
Oh, I have 2 minutes. So I'll not start with x2 today because x2 might take more time than this. It's simple. Okay. Now can you just give a guess? Can you just please try in your home? How do I really do this x2? X2 means I have to count both. So only difference will be what? Do I require this AND gate? Do I require this AND gate? Why? Because if I just count previous of A, present of A, it's going to give me both the transition, T1 as well as T2, right?
Yes, sir.
So do I really require this AND gate?
No.
No, right? I don't require this AND gate. Now for the direction, I have to consider both T1 as well as T2. So you find out like how do I really understand the direction. Okay? Right. Clear? Right? See, if you don't understand, please ask me. Okay? I don't know whether